All right, so now we've looked at the quincunx to simulate the spinning of a coin. So that's just a single action. Now, let's go back to Mendelian segregation and see what we need to do to expand on the quincunx, to expand our model to handle something a little bit more complex. So let's build up. So here we have got two actions going on. First, with the sperm, we can spin a coin there to see which one of the capital A or the little a gets attached to the egg. And at the egg side, we spin a coin there too, with probability of half, to see whether the sperm will attach to the capital A or little a. This is like saying, all right, decide here first with one spin of the coin, and then decide there with another spin of the coin. And then we end up with this probability distribution. So we've got, you could say, two heads, if you will, head and the head on both coins, or a head and a tail on one coin, a head, on the other coin a tail, or tail, tail. And we see that the ratios are 1 to 2 to 1. And then we end up with the thalassemia as an application of this concept. We showed this last time. Okay, so let's go back to our quincunx. At a slightly more complicated quincunx, we've put in 2 rows. So now, let's roll it. Now we see the ball first bounces on the top peg and then on a peg in the second row. And to accumulate into the leftmost bin, you've got to bounce left, left. To accumulate into the right bin, you've got to bounce right, right. And in the middle, you either bounce left, right, or right, left. So looks like very much like the thalassemia situation. And what did theory tell us? Theory told us that we should get about a 1 to 2 to 1 ratio. So we should get a quarter of the time in there, half the time in the middle, and a quarter of the time on the right. And if we look at, these are 100, I left the 101st dangling, so 30 plus 49 plus 21 equals 100. We see that it's roughly that. It's roughly, I mean, to be perfectly that, it would have to be 25, 50, 25, but it's approximately that because it's random. We're dealing with a random phenomenon. And in the long run, if we let this go on forever and ever and ever, we might get the exact. But for now, we've got approximately this. So you can see how we can build up like this. So for example, we can now look at a 3-rowed quincunx. And let's just go to the fast. And now what's happening here, if you let it roll a little bit, is theory tells us that this one should look like the ratio of 1 to 3 to 3 to 1. Okay? So I tried to stop it at 160 because theory said that I should get a 1 to 3 to 3 to 1 ratio. So that's a total of 8. So this should be 1/8, 3/8, 3/8, 3/8, 1/8, sorry. So that's 1/8. And so that's why I stopped at 160. You can have a lot of fun yourself when you go to mathsisfun.com and play with this and see if you can stop it at 160. But anyway, getting back to the serious stuff. How did I get this? How did I say, oh, the theory said this? Well, the reason we did that, or the reason we know that, is something which we call Pascal's triangle. Incorrectly so, but we call it that. And you get Pascal's triangle by doing the following. Start off with a 1, and then put a 1 on either side. And then put a 1 and put a 1. And get wider and wider by putting your 1s. Then take the sum of the 2 and put in the 2. Then take the sum of these 2, put that there. Take the sum of these 2, put that there. And then take the 1, and then take the sum of the 2 is 4. Take the sum of the 2 is 6. Take the sum of those 2 is 4, and so on. And what do we get when we do this? We get what is called Pascal's triangle. And what these are, they are the coefficients that appear in the binomial expansion, say, of a plus b. This would be a plus b to the 1. This would be a plus b squared, which would be a squared plus 2ab plus b squared. And this would be a plus b cubed. And this would be a plus b to the 4th, etc. And so these numbers here give us these ratios. So remember, with the thalassemia, we had a 1 to 2 to 1 ratio. With the 3-tiered, we had a 1 to 3 to 3 to 1 ratio. And if you now go ahead and do it yourself, you'll check it out with the 4, etc. These are the theoretical, the mathematical answers we expect. Okay. Now, as I said, this is called, we call it the Pascal triangle, even though it was known even in Europe before Pascal's time. Tartaglia, for example, had this. But even it appeared really in Persian in the 11th century or so. Here it is in a Chinese text in the 14th or 13th, I should say. No, beginning of the 14th century in a Chinese text.